So until now, we have been told what kind of regression we have to use, right? So we've been told either it's a linear regression, it's a quadratic regression, or it's an exponential regression. But in real life, this doesn't happen. In real life, you're going to have to figure out what model is best to use, right? And there's different ways that we can do that, depending on what kind of, what do we have. So in the case of a table of values, you're going to have to examine the first difference, second difference, and the ratio and see which one is more closer to being constant. Remember that in real life, when you collect the data, right, they're not going to be like perfectly aligned, right? Even when you do your first difference, they're not going to be perfect. They're not going to be constant. It's not going to be 2, 2, 2, 2, 2, 2, 2, right? So it could be like 2, 2.1, 2.4, right? But back to 2. So it's averaging around 2, right? Or you could have, same with your second difference, right? Or your ratio. Your ratio could be, let's say, 0.35, 0.34, 0.36, 0.35, 0.34. Now this is almost constant, right? So you're gonna look at your data, and then the one that is closest to being constant, then this is what is gonna decide what your regression line is from your points, from the table of values. Now when it comes to Excel, how would you know? Okay, so you're gonna graph your points as usual on Excel with a scatter plot, and then you're gonna test your 3 different regressions. Okay, you're gonna test it with a linear regression, you're gonna test it with a quadratic regression, you're gonna test it with a polynomial regression, and then you're gonna look at your R-squared value. And the one that has the higher R-squared value, the one that's closer to 1, that's going to be basically the regression line that you are going to pick. Okay? So it all depends on your R-squared value. The closer to 1 it is, then this would be your choice. Okay? This is how we do it. So if we look at this example, right? So this example says our digital clock contains a capacitor for power during brief electrical outages. The table shows how the voltage in a capacitor decreases over time after a power outage. Which type of relationship seems to exist between voltage and time? Justify your answer. Okay? So since this is a table of values, the first thing that you want to do, you want to test your first, second, and ratio. Right? So we're going to test the first difference, second difference, and the ratio. So remember that your first difference is going to be the bottom minus the top. Negative 1.8, and then you're going to do 3.9 minus 5.2, so it's going to be negative 1.3, and then 3 minus 3.9, that's going to be negative 0.9, and that's going to be negative 0.7.
Why does it say 7.9?
No, that's 7 minus 9.
Oh.
At first I started showing what I'm doing, but then after So what can you tell me about the first difference? Does it seem like it's almost constant or no? They're all over the place, right? It's decreasing, right? So negative 2, negative 1.8, negative 1.3. So it doesn't look like it is constant, right? So we're going to have to anyway test the second difference. And the second difference, you're going to subtract negative 1.8 minus negative 2, right? So that's going to be 0.2. And then you're going to do negative 1.3 minus negative 1.8. So that's going to be 0.5. And then when I do 0.9 minus negative 1.3, that's going to be 0.4. And then when I do negative 0.7 minus negative 0.9, that's going to be 0.2. the second difference, it doesn't seem like it is constant. So let's test the ratio. Now when you do the ratio, remember that you're gonna have to go back to your original y values, and then you're gonna have to divide y2 by y1, right? Remember, back to the original. So 7 divided by 9, that gives me about 0.8. 5.2 divided by 7, that's going to be 0.7. 3.9 divided by 5.2, that equals 0.8. 3 divided by 3.9, that equals 0.8. And 2.3 divided by 3, that's going to be about 0.8. So if we're looking at this one, right, our first conclusion that we were able to make is that the first difference is not constant. Therefore, this is not linear. You guys agree with me?
Yeah.
Okay. The second difference was not constant as well. Again, I can say that it is not. Now, what can you tell me about the ratio?
Ratio constant is 1.
So it's almost constant, right? Remember, our data are not gonna fit perfectly. So when we do the ratio, or when we do the first and second difference, they're not gonna be perfectly constant, but they're gonna be around, like almost constant, right? Yes, this is 0.7, but remember that these are all rounded, right? So we're gonna say that this is almost constant. And then we're gonna say that there appears to be an exponential relationship. Since this is a decay factor, right? If you look at this, this is decay because it's between 0 and 1. Since the decay factor are approximately constant. So are you guys okay with this? So even though your answer, they're not going to be perfectly constant, it's still going to be an exponential relationship.